Hello guys, welcome back to the Let's Crack ID. Today, I'm going to talk about how architecture decision matters. Yes, every single one. It wasn't a outage or incident. It started as a preparing a DR environment for your primary site. So, let's see how SRE helped to resolve it. Let's check it out. We were building a DR environment for our app in GCP alongside our on-premises setup. The goal was very simple. If on-prem goes down, cloud takes over safely, same performance profile. As soon as we complete the DR infrastructure and the application deployment, as a part of DR validation, we ran identical load tests. Same code, same test, same target numbers. And that's when we saw it. GCP wasn't consistent. GCP was about 18% slower than the on-prem. Yes, weird. It's not usual. And it's not even a tiny difference. Big enough to make us stop and say, okay, something is not right. At that point, we didn't know what was wrong, so we did what every SRA team does first. We assumed it had to be something practical and fixable. We didn't jump to the big conclusion. We went after the usual suspects. We gave more CPU and memory to the NGINX. We checked whether NGINX was a bottleneck. We tuned workers, connections, and the buffers. We even looked at the backend tuning. And yes, we got some improvements, but the uncomfortable part was the gap was still there. Cloud was still behind. At that point, the next obvious question was, are we even comparing the same thing? So we turned our attention to the test itself. We revalidated the tests. We verified the request makes, concurrency, and the rates. We fixed the test artifacts. We did the true apple to apple runs. And after all that work, the result was still the same. GCP was consistently behind. Now, things were getting interesting. We had tuned the system, verified the test, and the gap still wouldn't go away. So we stopped staring at the CPU graph and the test configs and started staring a different question. What exactly is happening to our request? That's when we finally looked at the request path. And that's where the story finally clicked. We discovered that in GCP, the internal load balancer had session affinity enabled. The ILB was seeing most traffic coming from the NGINX. And because of that, a huge amount of traffic was getting pinged to a one backend. In other words, on-prem traffic was spread across many servers, and in GCP, we were accidentally overloading one backend and underusing the rest. So GCP wasn't slower. We were just not using the backend pool properly. At that point, it was clear this wasn't a tuning problem anymore. So instead of tweaking more knobs, we made a bigger call. Stop doing stickiness at the ILB, match the load balancing behavior to the on-prem, and we moved session control to the NGINX, where we can see it, the reason behind, the reason about it, and control it precisely. We changed the traffic flow to external load balancer to the NGINX, and NGINX was load balancing traffic to the backends. We switched from IP hash based stickiness at the ILB to the NGINX cookie based session affinity. Now, let's take a look at it how the flow looks like. First request is balanced normally across the pool. NGINX picks a backend using its normal algorithm. Then NGINX sets a cookie in the response, something like set cookie serve to the backend -3. On the next request, the client sends that cookie back, and NGINX reads it and route directly to the same backend. So keep the session stickiness, but we don't break the distribution. The key difference is where the decision is made and what signal is used. With the load balancer affinity, the decision is based on the network level signals like IPs and ports. If most traffic appears to come from the one place, you can accidentally collapse traffic onto one backend. But with the NGINX cookie affinity, the decision is based on real application sessions. New sessions are still spread evenly across the pool. Only after that, each session stays sticky to its chosen backend. So, new load stays balanced, existing session stays stable, and you don't turn a cluster into single overloaded machine. And guess what? After this change, something interesting happened. Not only did GCP catch up, it actually ended up about 23% faster than on-prem. And that is expected because now all backends were being used, parallelism was back, and the cloud environment could finally show the real performance. So, the lesson from this DR exercise is simple. We didn't fix this by making server bigger. We didn't fix this by tuning the tests. We fixed this by making the architecture and the load balancing behavior truly equivalent. And that leads to a classic SRE rule. If two systems have different traffic shapes, your benchmark is lying to you. So, what started as a DR test got turned into performance incident, and changing the architecture pattern gave us the cloud faster than the on-prem. That is the reason every architecture decision matter. Yes, every single one. Thank you and stay tuned for the next outage video.